In this video, we're going to go through ideal gas law. So two things that we need to recall before we get into this. First of all, volume and pressure of gases are inversely proportional. So as the pressure increases, the volume is going to decrease. As the volume increases, or rather, while the pressure decreases, the volume will increase. Okay, so let's just talk about it in terms of a balloon. If I have a balloon here, if I increase the pressure on the balloon, my volume is going to decrease. The balloon will get smaller. If I took the balloon into outer space where there isn't a lot of pressure, that balloon would have lots of room to expand and it would get bigger. Okay, so pressure and volume are inversely proportional. Volume and temperature are directly proportional. So that means as the temperature decreases, the volume will decrease. I take a balloon outside on a cold day, that balloon is going to shrink. If I take that balloon outside on a hot day, or if I take it back inside after it's been cold, the volume of that balloon is going to increase. So two things we need to recall before we move on. All right, so let's talk about Avogadro's principle. Yes, it's the same Avogadro that developed the 6.02 times 10 to the 23rd. That same guy. So Avogadro's principle is equal volumes of different gases at the same temperature and pressure contain equal number of particles. So I have 4 different balloons here. One with helium, one with argon, one with nitrogen, one with oxygen. I have 1.5 liters of each. And guess what? They all contain the same number of particles. And for that volume, they contain 6.7 times 10 to the negative 2 moles of gaseous particles. And that's because they're at the same temperature and the same pressure. So when we talk about standard temperature and pressure, or STP for gases, that's 0 degrees Celsius and 1 atmosphere. 1 mole of any gas particle will occupy 22.4 liters at standard temperature and pressure, and it will contain 6.02 times 10 to the 23rd gas particles. So again, that's Avogadro's principle. Yes, same Avogadro. So this is ideal gas law. PV equals nRT. Pressure stands for, P stands for pressure, V stands for volume. The units of pressure are atmospheres. The units of volume are liters. N will be the number of moles. T stands for temperature, and we're going to use the units of Kelvin. Okay. And then R is our constant. Okay, depending on our units, but for these units that we're going to be using, this is our R value, 0.0821 liters times atmospheres over Kelvin times moles. Again, that's our proportionality constant here. So let's look at an example. In this example, it says an 8.5 liter tank contains helium gas at 16.9 atmospheres and 25 degrees. How many moles of helium are available for making balloons? Okay. So for this example, we are going to set it up using our PV equals nRT equation. Now, it's asking how many moles. So the way that I like to work these problems is I like to do the algebra first. So we're solving for n. So to rearrange this equation to get n by itself, I'm going to divide both sides by RT. Now you could just plug in your numbers and work it that way, but I find it's a lot cleaner to do the algebra first and then plug in your numbers. So if we rearrange this equation, we get n equals PV over RT. So let's go ahead and start plugging in some numbers now. So P, our pressure, is 16.9 atmospheres. Our volume, in this case, is 8.5 liters. Our proportionality constant is 0.0821. I'm going to leave the units off. And then finally, we have our temperature. Now, it's in Celsius, and we need our temperature to be in Kelvin. So 25 plus 273 will give us our temperature in Kelvin. So that will give us 298 Kelvin. So again, we always want to make sure that we're converting to Kelvin. So 298 Kelvin. Okay, when I put this in my calculator, I end up with 5.9 moles. Okay, be careful with your significant figures. I have 2 significant figures here. I have 3 significant figures here and 2 significant figures here. So I want to round my final answer to 2 significant figures. All right, let's look at our next example. So I would just want to write down really quick that we solved. So in the previous example, it says an 8.5 liter tank contains helium gas. How many moles of helium are available for making balloons? And we figured out that we have 5.9 moles available. So we have 5.9 moles. Okay, so it says if all of the helium is used to fill 1.5 liter red balloons at 0.99 atmospheres and 32 degrees, how many balloons will you end up with? Okay, so let's take a look at our equation, because it's not explicit what variable we're solving for. So we have moles. Obviously, we have our proportionality constant. We have a temperature. We have a pressure. We also have a volume, but be careful here. It says if all of the helium is used to fill 1.5 liter red balloons, how many balloons will you end up with? So we're actually finding out our volume here. We're figuring out the total amount of volume that we can fill with the amount of helium that we have. So let's rearrange our equation. To get volume by itself, we're going to divide both sides by P. Okay, and then let's plug in what we have. So we have 5.9 moles, our proportionality constant, and then our temperature. 32 plus 273 gives us 305. And then our pressure is 0.99. Okay, so when we do the math here, we end up with 149 liters. But that's not what the question is asking for. The question is asking how many balloons will you end up with? So we know that each balloon will hold 1.5 liters. If we divide 149 by 1.5, we end up with about 99 balloons. That's a big party. All right, let's move on to the next one. It says an unknown gas is collected in an 850 milliliter vessel at 1.02 atmospheres and 23 degrees. The evacuated vessel has a mass of 138.45 grams, and the vessel and gas have a combined mass of 140.12 grams. Find the molar mass of the gas. All right, well, we've got a lot of information here. We have an atmosphere. We have a temperature. What else do we have? We have a volume. So we need to do a couple of conversions first. So 850 milliliters divided by 1,000 gives us 0.85 liters. And then also 23 plus 273 gives us 296 Kelvin. So the variable we're solving for here is going to be N. That's the only variable that we don't have. So if I rearrange my equation for N, I get PV over RT. Let's plug in what we have. So our pressure, 1.02 atmospheres. Our volume, 0.85 liters. our proportionality constant, and then our temperature is 296 Kelvin. So here, if we solve for n, we get 0.0357 moles. Okay, now it's asking to find molar mass. Okay, and molar mass is the mass per mole. So if I know the mass, oh, hold on, we have two masses here. We have the evacuated vessel, and then we have the vessel and the mass. So we want to subtract those two numbers to get just the gas. So it's going to be 140.12. That's the mass of the vessel and the gas, minus the empty vessel, which is 138.45, over the number of moles we just solved for. And here we get 46.8 grams per mole. All right. One more. All right, it says an unknown gaseous hydrocarbon has a density of 3.24 grams per liter at 1 atmosphere and 28 degrees Celsius. Find its molar mass. Okay, so again, we need to find N first. So N is grams over the molar mass. Okay, or grams over grams per mole, if we're using our units here. Density, P, is equal to mass over volume. Now, if we go back to our ideal gas equation, PV equals nRT, let's plug in some variables that we have. This one's going to be kind of a unit nightmare here. So we can substitute in for N. So this is rho. This isn't actually the same P. This is our density P, not the same as our pressure P. So if we substitute in our N, which we solve for, which is, let's see, it is mass over molar mass, or grams over molar mass. So this will be, let's write it that way. Let's write it as mass over molar mass times our proportionality constant and temperature. Okay. Now, it's asking us to find molar mass. It's asking us to find this. So we have to be a little creative here with our math. So let's multiply both sides by molar mass. So if we do that, our molar mass will cancel here and here. And then at the same time, because we're crazy, let's divide the PV out so we get molar mass by itself. And I'll clean up my units here in a second. So this goes away and this goes away. So now what we've done is we've rewritten our equation, and we have this. We have molar mass equals the mass times RT over PV. So let me rewrite that. So mass times RT over PV. Okay, now, I know you might not see it, but rho, our density, is mass over volume. So what I can do is I can take these two terms right here, since everything's being multiplied, and I can replace that with my density rho. So some creative substitution going on here. So molar mass equals rho, I'll try to write that P a little different, times R times T over P. And again, that's not the same P. That's our density P. Okay. So let's plug in all of the numbers that we have. So we have our density, which is 3.24 grams per liter. Proportionality constant. And the temperature, which 28 plus 273 is 301 Kelvin. I'm running out of space for units here. And then let's divide that by the pressure, which was 1 atmosphere. So if I do all the math here, I get 80 grams per mole. That's my molar mass. Okay, now, again, I'm a huge advocate for doing the algebra first and then plugging in your numbers. And as you saw from this problem, had we plugged in the numbers, it would have been an absolute mess if we tried to get our variables by themselves. So this one was a little tricky, but totally reasonable, totally doable. So do the algebra first.